It's my pleasure to introduce Federico Ardila, who's a professor at San Francisco State University. His research is in combinatorics and its connections to geometry, algebra, topology, and applications. And today he's going to be telling us about a tale of two polytopes, the bipermutahedron and the harmonic polytope. Okay, take it away, Federico.
Okay, thank you all so much for the invitation to this conference. It's really wonderful. I'm always really inspired to see how everybody is adapting to these strange times, and I really thank you all for being here because I know that times are challenging. I know that there's a lot more demands on your time and your energy than usual, and so it's very meaningful that you're here to talk about mathematics. Okay, so let's see. So I will be talking to you today about two polytopes, the bipermutahedron and the harmonic polytope. Okay. So sorry, I'm just working on a small screen here, so I'm trying to figure out where to put things. Okay, let's do this. Okay, so the conference, so the talk is going to have two parts. So I'll begin by telling you kind of an origin story of where these two polytopes come from. They come from a project with Graham Denham and Juni He on matroids, and I won't really talk about matroids very much at all, but I want to kind of at least say that where the origin of these things come from, even if the polytopes in themselves are not matroidal. And then I will tell you about the two polytopes, first the bipermutahedron and then the harmonic polytope. And the work on the bipermutahedron, part of it is in my joint paper with Graham Denham and Juni He. And then the other part is in this paper, which is just studying the bipermutahedron. And that's a solo paper. And then, I don't know why this, let me get this out of the way. I don't know why the preview is acting all weird. Is this looking okay if I show it to you like this? Okay.
Yeah, it looks good.
I think this is the way that I'm actually going to be able to see your faces, and I think that's great. Cool. So yeah, as I was saying, the work on the first polytope is partly with Graham Denham and Juni He, partly on a solo paper, and then all the work on the harmonic polytope is with Laura Escobar. Okay, and so I mentioned this is the plan, the origin of this story. Then I'll tell you about the bipermutahedral fan and the bipermutahedron, and then I will tell you about the harmonic fan and the harmonic polytope. Okay. And at any point, feel free to ask me any questions that you have. And let me just make sure that I have the chat in front of me. Okay. So okay, so very briefly, I'll tell you an origin story of all of this. And I should say that if you're interested in a longer version of this story, I have a talk on my website where I tell this part of the story. But just to tell you where this comes from, for only one slide, I'm going to talk about matroids, and I don't really want to define them because that's not the main point of this talk. But the idea of where this comes from is that given a matroid, there are two vectors that we associate with them: the f vector and the h vector. And these are some kind of numerical invariants that tell you a lot of information about the matroid. And there were these conjectures, these very old conjectures, that both the f vector and the h vector are log concave, and in particular unimodal. So unimodal means that if you look at them as a sequence, they go up and then they go down. Log concave means that their logarithms form a concave sequence, and that's a more stronger statement. Okay. One reason that we like thinking about log concavity in combinatorics is because when we see things that are log concave, Usually the explanation is either quite quick or quite hard. And in a problem like this that has been open for many years, I think it was kind of understood that it was going to take some new ideas. And usually the way that law concavity is proved is by forming a new connection between your objects that you're trying to figure out there's some combinatorial object. And usually the law concavity comes from outside of combinatorics through ideas from representation theory, through ideas from algebraic geometry. And so that's one of the reasons that I think we in combinatorics are so interested in law concavity. I mean, it's nice to be able to prove that a sequence goes. If a sequence goes like this, you want to understand why a sequence goes like this. That's just human nature, at least mathematician nature. But this kind of thing usually reveals some deeper connections with other areas of mathematics, and that was the case in this situation. So the first. I mean, really, the big breakthrough came from Jun Ha's PhD thesis, where he proved a very important case of the first conjecture and kind of opened up the way to a lot of the other results. And I'll just say some words of some of the connections. So in the first paper by Adiprasito, Ha, and Katz, the way that they proved this first conjecture is through these tools: tropical geometry, algebraic combinatorics, and combinatorial Hodge theory. The thing that's relevant here is that everything takes place in this kind of ambient space. There's a geometric space associated to a matroid where these computations take place, which is something called the Bergman fan of the matroid. Okay, and an important observation is that the Bergman fan lives inside something called the permutahedral fan or braid fan. Okay, and this is a very classical fan. This connection was done in a paper that I wrote with Carly Clivens in 2006. And then to prove this second conjecture, we had to basically work, instead of with a kind of ordinary tropical geometry, we had to take up a Lagrangian tropical geometry point of view. And that meant that some of the things had to change. And in particular, we had to, instead of a Bergman fan, use something called a conormal fan associated to a matroid. And instead of the permutahedral fan, we needed to find a fan for which we had two candidates: the bipermutahedral fan and the harmonic fan. Okay, and so if you don't have a lot of experience with matroids, that's totally fine. The point that I'm trying to make here is simply that these two objects, which are the main objects of my talk, were supposed to be some kind of analogs of the permutahedral fan for this setting. Okay. So that's the origin, and I can tell you more if you, at the end if you want to know more, but for now let's just talk about the polytopes. And in particular, let's talk about this permutahedral fan, which is what we're trying to extend. Okay. So the permutahedral fan looks like this. So I'm living, for a moment, let's talk about R to the n. Let's say that I'm in R to the n, in this case in R3, okay? And then I'm going to consider all the hyperplanes of the form xi equals xj. Okay, so for example, if I'm in R3, then I have x1 equals x2, x2 equals x3, x1 equals x3. Okay, I'm doing this over the real numbers. And this is important because over the real numbers, when you have a hyperplane given by one linear equation, then that hyperplane has a positive side and a negative side. And you should realize that this has to do with the fact that we're working over the reals, because the reals have positive and negative numbers. So over the complex numbers, this is not the case. But over the reals, each hyperplane breaks me up into two regions, okay? And that means that if I look at my hyperplanes and I kind of pull them out, that's going to separate my whole space into regions, in this case 6 regions, okay? And for the hyperplane arrangement, these regions are not difficult to describe because, for example, this hyperplane right here is the hyperplane x1 equals x2, okay? We should remember that this is in 3 space, so this is actually a plane, but you're kind of looking at it from the edge, so you only see this line, but this is really a plane. And then this is where x1 is bigger than x2, this is where x1 is smaller than x2. Okay, so in order to know what side of the hyperplane you're on, you need to know, is x1 bigger or smaller than x2? To know what side of this one you're on, you need to know the order of x1 and x3. And to know which side of this one you're on, you need to know the order of x2 and x3. And so that means that the regions of this arrangement are basically going to correspond to all the ways of sorting out those pairwise orders. In other words, the permutations. So for example, here, this region right here corresponds to the points which have x2 bigger than x1 bigger than x3. Okay. And so this is what I'm calling the stratification of the space in terms of the relative order. x1 is bigger than x2 is bigger than x3, for example, corresponds to this region right here. And something like this, okay, this edge, this kind of infinite ray, x1 and x2 are tied, right? So they're actually equal to each other, and they're bigger than x3. So that corresponds to this. And so I'm splitting up my whole space, in this case r to the 3, in general r to the n, into strata, and strata are just pieces. The idea is that the pieces are in correspondence with ordered set partitions. And an ordered set partition is a way of taking the numbers from 1 up to n and splitting them into sets in some order. So in this case, I'm taking the set 1, 2, 3 and splitting into sets 1, 2, and 3. But those sets are ordered, meaning that I have to say first it's a set 1, 2, and then it's a set 3. Okay? So those are the ordered set partitions. There is one kind of small detail that I want to point out that is not too important now, but is going to become important later, which is that these 3 hyperplanes have a line in common that is kind of looking into your eye, right? From your eye to this point, there's a line which is the line x1 equals x2 equals x3. And so really this is more like a, in fact, that's why it's called a fan, because it's like the thing that you fan yourself with, right? But what I want to do is that I want to quotient out by that line just so that I'm able to draw these pictures. And so really, like, this is R3, but I'm actually quotienting by R, so that's why I'm saying R3 modulo R. If you prefer just thinking about this as R2, that's fine. It's really just a 2-dimensional real vector space. Okay. So this is the permutahedral fan that we are trying to extend, and I want to think of it in a specific way. There's a model that I want you to think about, which is that you have 3 points that are moving around on the real line. Okay, so here I have 3 points that are kind of dancing around this line. And for example, when point 3 is here, point 2 is here, and point 1 is here, then x1 is bigger than x2 is bigger than x3. So this configuration of 3 points is going to correspond to some point over here, right? Some point over here corresponds to this configuration. And as I'm walking around this chamber, I'm basically moving those points around, but they have to stay in the order that 1 is bigger than 2, bigger than 3. Okay, but you can kind of imagine as I'm moving my mouse around this picture, you can imagine those points below moving with my mouse, right? And so, for example, when I move my mouse over to this line, and I start moving it along this line, then this is where x1 is equal to x2 and is bigger than x3. So it starts corresponding to those configurations on the right. Okay. When I say that I'm quotienting by R, that I'm doing everything mod R, what that means is that I'm considering 3 points moving in R modulo common translation, and that means that if I look at 3 points and I consider that one configuration, if I move all of them at the same time with the same speed and at the same distances, then I think of that as the same configuration. Okay, so I'm thinking of R to the n mod R as the set of n tuples of points moving around a line, modulo the fact that like global translation is not really going to do anything. Okay, that's how I want to think about this permutahedral fan. Okay, and so in general, I mean, one reason that I want to do that is that it allows me to do this in higher dimensions. So if I want to think of the permutahedral fan as a moduli space, which is just what I did in the previous slide, then I can define it just as I did. I am in n-dimensional space and I look at all these hyperplanes. But if I want to be able to draw pictures, actually this model is very useful, which is that I think of this space as an n-tuple of points moving around the real line, modulo common translation. Okay. And again, the stratification is basically that I'm looking at that whole n-1 dimensional space and splitting it up into pieces according to the relative order of the points. And the strata, again, are ordered set partitions, okay? Where I basically go from right to left and I say 3 is the biggest, then 2 and 8 are tied, then 0 and 4 are tied, and so on. Okay. So this is how I want to think about this permutahedral fan as a moduli space. So let me pause for a moment and see if anybody has questions about that, which is very much a classical story, but I think I'm telling it in a slightly unusual way. So if you have questions, especially if you've never seen this before, I'm happy to take questions about it. Okay, so I don't see. Oh, okay. Sorry, I'm looking at the wrong place. What do we mean by the term fan? What we mean by the term fan, thank you for the question, Nicholas. So in order to say what fan is, let me first say what cone is. So a cone is something like this right here, which is basically it has some rays, and then it's like everything that's in the direction of those rays. Okay, so this is it's a cone. Another way of saying it is that it's intersecting hyperplanes going through the origin and seeing what's over there. And when I say fan, what I mean is a bunch of cones glued together. And so this is literally like a fan that you fan yourself with, not a ceiling fan, but like a flamenco dancer fan, where you have like, you know, one little flat part and then another flat part next glued to it and another one and so on. So it's basically gluing a bunch of cones along their common faces. That's what I mean by that. Okay. Thank you for the question. These fans are very different from flamenco fans, because flamenco dancer fans, because flamenco dancers fans are only occupy part of space, and these fans occupy the whole space. Right? This is called a complete fan, and that's important. Okay, so the reason that I talk about this permutahedral fan in this way is because I am going to now try to introduce a different fan, which is the bipermutahedral fan, which I cannot draw anymore. So I showed you, I mean, this thing gets high dimensional very quickly. And so really I have to think about it as a moduli space if I want to be able to do examples. Okay, so what is the bipermutahedral fan? So it's going to be a fan. Similarly, it's going to be some kind of model for n tuples of points. The difference is that now the n tuple is allowed to move in R2. Okay, so the points are actually moving around the plane. And so here is one configuration of points that lives in here. Okay, if you're paying very close attention, what I mean here is r to the n mod r times r to the n mod r. And what I'm doing is that I'm basically taking the x and y coordinate, and so the x coordinates I'm putting it into a vector here, and the y coordinates I'm putting it into a vector there. Okay, but really I find it much more useful to think about it as my space that I'm living in is the space of n tuples of points moving around R2. But again, modulo common translation. So if you shift the whole plane, that doesn't change the configuration.
I think there's another question, which is there a notion of fan? Is the notion of fan related to triangulations?
Yes, thank you for the question, Gaurav. So for example, this is an example of what we would call a triangulation of the plane into cones, and it's called a triangulation because the cones are like triangles but unbounded. They're simplicial cones. So yes, this is related, but it's a little bit more general because in triangulations you only use triangles or simplices in higher dimensions, and here I'm allowed to use anything. So it's more like a polyhedral subdivision, a little bit more general than a triangulation. Thank you, Gaurav. Okay, so I want to stratify, and the thing is that now it's not so clear how I'm supposed to stratify, because before I was stratifying the points from left to right, but here there's no left to right. Okay, so we're going to stratify in a way that it might seem a little bit unusual, and I just want to point out, like, this wasn't like, oh, we just dreamed this up out of nowhere. This is something that the Lagrangian geometry that I was mentioning dictated. Like, this is probably what we should do. Okay, and so I'll tell you how we stratify. What we do is that we say, okay, first of all, we look at those points and we take a diagonal line at a 45-degree angle and at a minus 45-degree angle and push it up until it hits the configuration. Okay. and I'll answer your question in a second, Vishal. So I swing it up until it hits the configuration. Okay. And in this case, it hits points 1 and 5 simultaneously. Okay. Then I'm going to project all those points vertically and horizontally on that support line. And then I'm going to mark them. So for example, like the shadows of the shadows of P0 get marked 0 and 0. For example, this is called 0, 3, 5 because the vertical shadow of 0 falls here and the horizontal shadows in 3 and 5 fall here. Okay. And so basically, like when you look at the horizontal and vertical shadows of the points, you get some markings and sometimes you get some coincidences, as it happens here. And then what you do is that you record the relative order of those things on the line. So you say, okay, 3 and 4 landed first, then 2, then 0, 3, 5, and then 1, and so on. Okay? So that's the strata. And so basically, if two configurations of points, when I do this process, they lead to the same order, then those points are going to end up in the same little piece of that diagram. So again, I'm looking at this huge space, and I'm splitting it into pieces, where in each piece you get the configurations that lead to some particular bisequence. Okay, it's a little bit more abstract, but this is how this works. Okay. And to answer your question, Vishal, this ends up being a little bit more subtle than a product of a pair of hyperplane arrangements. In fact, there are no hyperplanes here anymore, which is what makes this a lot harder. Okay. Okay. So this is the bipermutahedral fan. Let's talk a little bit more about what these stratas are. Okay. So, for example, so Jia1 is asking, can I say a bit more about configurations having the same bisequence? For example, let me take point P0 and move it up vertically. If I do that, nothing is going to change except that this label 0 moves over there, but it stays in the same place. Okay, so that's still the same configuration. And so if I move the point P0 up, I'm going to get the same bisequence. If I move it down, I'm going to get the same bisequence, the same one, until I hit this point. And then when I hit this point, all of a sudden the shadow of 0 is going to land here onto the bisequence 0 to 4, blah, 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 blah. And so that's a different bisequence. And so that means that I have fallen out of that region of the fan. Okay. So that's how this works. What are these bisequences? So these bisequences are not something that were defined before. We had to kind of think, okay, what are they? They're easy to describe. So each number has to appear once or twice. If you think about it, that makes sense because for example, the number 2 appears twice because it's the vertical and the horizontal shadow, right? You cannot appear more than 2 times. But there are some elements that appear only once. For example, 1 appears only one among the labels, and that's because P1 is on the support line. P5 is also on the support line, and that's why 5 appears only once. Okay. And so these sequences basically are all the sequences that contain each number either once or twice. But there has to be at least one number that only occurs once because the support line hits at least one of the points. And so that is going to appear once. Okay. So this is the definition of a bisequence. Okay. And so this begins to let us understand the combinatorics of this fan. Okay. So again, let me pause and see if people have questions about the fan. I'm about to talk about the polytope. Thank you for your questions so far about the fan. I should say, by the way, that I've thought about this fan for years, and so I've grown accustomed to it, but this gave me a headache when I started thinking about it. I want to say that out loud. If you have a headache, you're on the right track. And maybe, like, if you're not understanding all the details, the point is basically these points are moving around, and all you care about is like what are the shadows that they're casting onto that line. Okay, that's what you're paying attention to. The vertical and the horizontal shadows that they make onto this diagonal line. There is absolutely a bijection between this fan and bisequences, and there's actually no constraint. And so we will talk about that in a second. Yeah. Okay, so now let's go from fans to polytopes. So here's a fan. And I want to know if it comes from a polytope in the following way. So I'm going to say some things about polytopes, and I know that probably many of you don't usually think about polytopes very much. So if you have questions about that, this is a good moment to ask. Okay. So we have a polytope, right? So this is an example of a polytope, and when I say a polytope, I just mean you take a bunch of you take a region that is bounded by flat constraints, okay, by hyperplanes. Now, when I look at this, I have some notion of what the faces are, but if I want to do this in higher dimensions, I have to think about what this means. So, for example, how do I know that this is a face of this hexagon? One way of thinking about that is that if I point my finger, and I don't know which way I'm pointing in your screen, so maybe you can, I don't know if you should do my left hand or my right hand, but one of these hands is pointing towards that, this face, right? For me, it's my left hand, so I'm going to go like this. So my left hand is going in this direction. This is my left hand. And this is the farthest part of the polytope according to this direction. And so the one way of saying that is that I take my vector W, which is given by my finger, and then this is the face of P that W maximizes. So that's how I know that that's a face. And the definition of face is whatever maximizes your finger when you point at it in some direction. If I point my finger up a little bit further, like over here, then the farthest part of this polytope, according to this direction, is this point. Okay, then what I do is that I now look at all the various faces of this polytope, and I say, okay, what are the directions that maximize this line? They are the horizontal directions to the right. So all of these points give me the same face. All of these points give me the same face. If I point in this direction, the farthest face that I get is this one, okay? And if I look at any point in this region, and I take the dot product with the points in this polytope, this is the only place where that product is going to be maximized, okay? And so in any of these directions, the maximal point is this one, okay? And I basically keep doing this. So for every face over here, I say what are the fingers that point to that face, and I put them all in the same cone, okay? And so this is another example of a fan made of cones, where each cone consists of the directions that point to a particular face, okay? If you're used to constructing the dual graphs, this is kind of the same thing, right? I'm just kind of putting a point inside a region and connecting them. And this is kind of a higher dimensional analog of that. It's not a perfect analogy, but if this is the first time you're encountering this, this is a somewhat useful analogy, okay? So when you have a fan, a natural question to ask, if you study the kinds of things that I do, is whether this fan comes from a polytope. This ends up being a very beautiful, useful question. And in particular, if you're interested in the connection between polyhedral geometry and toric geometry, toric algebraic geometry, this becomes a really central question. And it turns out to be very useful if your fan comes from a polytope. Okay? And in particular, for the application that we had in mind to prove the log concavity of this H vector, it is absolutely essential. It wasn't enough to construct this fan. We needed it to come from a polytope, okay? And so actually, like, we were happy that the fan had some nice properties, but also we needed a polytope to go with it. And so that's where the bipermutahedron comes in, okay? Again, this is inspired by the permutahedron, because the permutahedral fan is called the permutahedral fan because it is the normal fan of a polytope that's called the permutahedron. kind of a mouthful. But basically what this says is that the permutahedral fan that I started with comes from a polytope, which is called a permutahedron. And so one of our theorems is that the bipermutahedral fan also comes from a polytope. In other words, this fan which I showed you comes from a polytope, and that occurs in every dimension. Okay. And I'm putting two citations here because the first construction of this polytope was I don't know, I liked it. I thought it was beautiful, but it was intricate. It was pretty intricate. And it described the vertices. So it said, okay, if you want to describe a polytope, you can say, what are the vertices of that polytope? But whenever I would give this talk, or whenever everybody would look at this paper, people would say, like, that's a very messy polytope. Like, can you do better? And in this newer paper, because this paper is actually, like, in some sense, we proved these things in like 2015, and it took a while to write it. 2015, 2016. In this newer paper, I found this description, which is the description of inequalities of the polytope. Okay, and if you've looked at inequality descriptions of polytopes, this is a very simple one. This is about as simple as it's going to get. And from this, I've become pretty convinced that this is probably the nicest realization that we're going to find of a polytope, such that this is the normal fan. I should say there's never one nicest construction. One thing that I do prove in this paper, for example, is that it is the most symmetric one. Okay, so there is a sense in which this is a good construction. Okay, there was so I want to address next the question of Gaurav, which is about I like geometry, but I also like counting. I'm also that kind of combinatorialist. So one thing that I like doing is counting the faces of polytopes. And there is a perfect bijection between the faces of the polytope, the faces of the fan, and the bisequences. Those three sets are in bijection. You can count any of them, and as you can imagine, for combinatorics' sake, it's best to count this one. Okay. I want to count them according to their dimension, right? For example, if I look at the vertices of the polytope, they correspond to the kind of finest bisequences, which we call the bipermutations, where every block has size 1. And those are not hard to count, and you get that the number of them is this. Okay, so this is the number of vertices of the bipermutahedron. The facets are the coarsest bisequences. They only have 2 parts, and those are also easy to count. Once you kind of get used to the definitions, if you unravel what this means, then you find that the number of these is 3 to the n minus 3. Okay. And we actually want the whole F vector. And so I want to be able to know, like, for each dimension, what is the number of faces of that dimension. And this is the kind of enumerative problem that I enjoy solving. So if I want to count the number of d-dimensional faces of the n-dimensional polytope, there's 2 variables, and so it's often very useful to put that into a generating function. In this case, it's useful to put it in an exponential generating function. And the theorem is that it's actually this very simple generating function. It's a very simple transformation of something called the 2-variable Rogers-Ramanujan function. And this 2-variable Rogers-Ramanujan function keeps appearing in papers. And I find it very interesting that it keeps appearing in different kinds of work that I've done. This is related to computing top polynomials of root systems, to computing arithmetic top polynomials of root systems. I should say that this was pioneered by Eunice Mpako Banda in her PhD thesis. I did some work on my PhD thesis, De Concini and Processi, and in a paper with Federico Castillo and Mike Henley, we found other connections to this, and so there's a lot of connections here. One reason is because basically this is a generating function for graphs, for complete graphs in some sense. Okay, and so one way of thinking about this is the generating function for complete graphs. But still, I think that there's some interesting connections there that there may be more to that than I understand at the moment. But anyway, the point is that the f vectors are given by this nice generating function. Okay, so we can compute the f vector of the bipermutahedron. One thing that is useful sometimes is to do this change of variables, where you take the f vector, you put it into a polynomial, but instead of putting powers of x, you put powers of x minus 1, and then you get some other sequence, which is basically a simple transformation, right? You can get f from h, you can get h from f. When you first see this, it doesn't seem very interesting at all. Like, what are you doing there? But the reason that this is a lovely transformation to do is, and it's, I would say it's only lovely if your polytope is a simple polytope. So I'll say what that means in a second. But if your polytope is simple, then it turns out that the sequence that you get h is symmetric. hi is equal to h d minus I. A simple polytope is, if you're in d dimensions, every vertex should have d edges. Okay, that's a simple polytope. In some sense, it's like a generic polytope in the sense that, like, you don't have too many things meeting at a vertex. So in some sense, most polytopes are simple. And actually, again, as often happens in combinatorics and in almost any part of mathematics, whenever you have a symmetric sequence, there probably is some sort of duality, whether it's an algebraic duality. Hi, cat. Your cats are very welcome. I want to say thank you for inviting your cat, Elizabeth. Whenever you have an equation like this in combinatorics, there's often some kind of algebraic manifestation of Poincare duality. There's often some kind of topological manifestation, and this does happen here. But to say it more simply, like, this is a simpler encoding because the f vector takes 2 n entries, and the h vector is going to be half as long because the first entries are going to be the same as the last entries. Okay, so that's like a nice shorter encoding of the f vector. I think that to the anonymous attendee, I think your two numbers are, yeah. You might be right that I might be off. I might have a small typo in my formula. Whoever anonymous attendee is. I'm happy to see that you're counting. You're like me. You see things, you want to count them. Okay, we call this the Eulerian polynomial, and the reason for that is I should have stated before this that there's a theorem that the h vector of the permutahedron is given by the number of permutations with a given number of descents. So you look at all the permutations and you see how many times do they go down. So a descent is a big number followed by a small number. And when you classify the permutations according to how many descents they have, this is called the Eulerian polynomial. And for the classical permutahedron, the h vector is that sequence. And here we have a similar theorem that for the bipermutahedron, the h vector is given by the number of bipermutations with I descents. And in particular, this gives you a combinatorial proof of this statement, because the things with I descents and the things with like I ascents have the same size. So that's what this says combinatorially. Okay. One thing that I kind of observed by looking at a bunch of numbers is that this sequence is log concave. And that's something that was known for the permutahedron, and so I wanted to show it for the bipermutahedron. How might we show that these numbers are log concave? And I tried and couldn't find an obvious proof. I got stuck, and this is something that kind of sat on my to-do list for a couple of years. Like, okay, maybe one day I should try to push harder, but I just didn't really have the right idea. So sometimes you just need to let a problem sit for a couple of years. and until you meet the right person that will provide the right idea. In my case, that was Katarina Johenko. So maybe I'll say that before meeting up with Katarina Johenko, I had discovered this other thing, which is that, so it's the following statement. When I was still trying to understand this bipermutahedral fan, I found a different model for it, which I will describe now. Let's take the standard triangle in R3. What I mean is take the point 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, that's an equilateral triangle in R3. And now you're going to take the product of n of those triangles. Okay, the triangle is two-dimensional, living in 3 dimensions. So this is going to be a 2n-dimensional polytope in 3n dimensions. Okay. And what I found is that actually it's possible to take that polytope, which a triangle is simple, but once you start multiplying it many times, it becomes more complicated. But you can take that big polytope and cut it up into pieces. And the puzzle that you get is combinatorially isomorphic to this fan that we're studying. Okay, so you can basically think of this fan as being a triangulation of this polytope. And one nice thing about the triangulation is that it's unimodular, meaning that every simplex in the triangulation has volume 1. Okay? I'll answer your question in a second, anonymous attendee. So then that means that I can think of I can think of this bipermutahedral fan that I'm trying to understand as being a triangulation of some polytope. Okay? The nice thing about that is that there is a nice connection with Ehrhart theory here, which tells you the following, that when you have a unimodular triangulation like this, then the H numbers of your triangulation are related to counting lattice points in your polytope. Okay, if you have ever done Ehrhart theory, this is the Ehrhart polynomial, and this is the thing that we're trying to compute. Okay, so I find this theorem really beautiful because the left-hand side is just combinatorics of counting faces. Right? This is the H polynomial that we're trying to understand, which counts the faces of our bipermutahedron. And the right-hand side is telling you count the lattice points in this polytope. And in 2 times that polytope, and in 3 times, you need to know that polytope times k, count the lattice points in there. It turns out the answer is this one. It's not hard to this is not hard to figure out once you get the right definitions in place. And so you get this interesting expression for this H polynomial. This is the Eulerian polynomial. Okay, and this is something that I knew some years ago, but I don't know. It seemed kind of cute to me, but I didn't know what it was good for. So that happened, and then what happened is that I was in this summer program, in the semester program in the Simons Institute for Computing in Berkeley, and there was a lot of discussion about polynomials with real roots. And Katarina Johenko gave this really, really beautiful talk, talking about many methods in which you can prove that a polynomial has all its roots real, which turns out to imply that the roots are log concave. So that the coefficients are log concave. So if you want to prove that a sequence is log concave, one thing that you can do is try to understand the roots of that as a polynomial. Okay. And once she gave that talk, I just knew, okay, Katarina is going to know immediately what to do. And we sat down first. I thought we were going to have coffee and talk about this, but I just showed her this formula. She said, yeah, that's real rooted and log concave, and she basically knew all the right tools to say, like, from this, if you know how to work with polynomials with real roots, you get that this polynomial has real roots, and therefore that H vector is log concave. Okay. And this is a little bit of what I was telling you, that sometimes when you want to prove that things are log concave, you need some unexpected connections, and this is one of those connections. Let's try to think of the roots of a combinatorial polynomial. So that's that. Okay, so I think that's all that I was going to tell you about the bipermutahedron.
I think,
yeah.
sorry. I think there's two more questions in the chat. One, we have an anonymous question. I don't know if you want to answer these now or later. Oh, so I can read.
Yeah, no, I can see them. So the first question: does it make sense to try to recover the bipermutation from the sequence of HIs? I'm not so sure because the HIs tell you about the whole polytope, but it doesn't tell you about individual bipermutations. Tell me if I'm misunderstanding your question. What do I mean by a fan being isomorphic to a triangulation of a polytope? What I mean is that there's a bijection. It's a little bit different because fans are infinite, triangulation. Fans are unbounded, triangulations are bounded. But what I'm saying is that there is a bijection between the faces of the fan and the faces of the triangulation, and that bijection preserves inclusions. And so basically combinatorially, the incidences are the same. It's just that one is unbounded and the other one is bounded. But that doesn't end up being that important if you want to count. Okay, so I expected that I would say much more about the bipermutahedral fan than about the harmonic fan, but let me tell you a little bit about the harmonic fan, which is going to be very similar. We start with the same thing. So this is going to be a different moduli space on n tuples of points in R2, modulo common translation. I do the same thing that I did before. I do the projections. I mark the same numbers. But then the only thing that I do differently is that I actually pay attention to like which shadows are horizontal and which are vertical. So I'm marking the horizontal shadows in black and the vertical ones in blue. I want to say right away that this marking is only a visual aid, but it's not more information because the horizontal marking always comes before the vertical marking. So you always know that the first eye is black and the second one is blue. So this is not additional information. It's just a visual aid. Because what I'm going to do is, with this same information, I'm not going to record the relative order of everything. I'm just going to record who are the points that landed on the diagonal, in this case, 1 and 5. I'm going to record the order of the blue things. So I record 1 and 5 are on the line. I record the order of the blue points and the order of the black points. Okay, so the order of the blue points is 3, 4, 2, 0, 5, and 1. And the order of the black points is 3, 5, 1, 2, 4, and 0. Okay? And I'm going to call that a harmonic triple, and I will explain why that's called a harmonic triple later. But basically, I am doing this, but I'm storing less information than before. And why is it less information? Because this does not know, for example, this does not know the relative position of a black thing and a blue thing. I'm only saying, okay, what's the relative position of the black things? What's the relative position of the blue things? But I actually forget, like, who was black. Like, I have no idea, for example, like, yeah, I don't know if I have a great example in here, but like, I don't know if blue 2 and black 4, which one is before or after which one. The harmonic triple does not know that. The bipermutation knew that. So that's why this is less information, okay? And what that's, okay, and I think this is what I was trying to explain here, but I think I already explained it. But the consequence is that the bipermutahedral fan refines the harmonic fan. So if you're used to that terminology, that's what that means. But that's just a restatement of what I'm saying, which is that the harmonic fan has less information, and the bipermutahedral fan has more information. So it has a more refined information. It has a more refined understanding of our configuration. Okay. And so this is the other fan that was a candidate for a possible an analog of the bipermutahedron. This one we also needed to know if it's polytopal, and this we managed to do with Laura Escobar. And so this is the harmonic fan in 2 dimensions, and this is the polytope, and these look very similar in 2 dimensions. So this picture and the picture I showed you earlier are similar in 2 dimensions, but after that they become very different. Okay. But the harmonic fan also comes from a polytope. Okay. Why am I calling it harmonic anything? It's because of this fact that was just really, really surprising to us, which is that, okay, the number of facets was 3 to the n minus 3, which is the same as before. That was not surprising. But when we counted the vertices, this is one of those moments where you just feed it into the computer, you get a sequence of numbers, you put it on the online encyclopedia, it doesn't find it, so then you say, okay, what hacks do I have to be? So they're like, what can I do this? And then eventually we discovered, like, wow, is this really the number of vertices? This makes no sense. N factorial squared times the harmonic sum. This does not look like the number of vertices of this polytope. And even proving it, I mean, I'm not going to say the proof is super hard, but it requires some ideas. This is, and I would say that it's still kind of mysterious, like why does the harmonic sum appear here? I want to point out that this is black. This is a black exclamation mark, so it's not part of the expression. It's not a factorial. It's a black exclamation mark. Okay. And again, I think that I have this kind of philosophy in my way of doing combinatorics. I love combinatorics and all its flavors, but my favorite flavor of combinatorics relates to algebra, relates to geometry, because I just find that when things have connections to algebra, to geometry, they end up having these structures that are just there, and it lets you discover them. So I think this is an example of something that, like, this is not what we were headed for, but somehow we realized, okay, there must be something natural about this polytope because it has such a beautiful structure. And so we were able to find the F vector. The H vector is not interesting because this polytope is not simple, so we didn't do that. And instead what we do is the volume, okay, which actually I want to say is something that I don't know anything about the volume of the bipermutahedron. And if you want my contribution to the open problem session, it would be to find the volume of the bipermutahedron. I don't know what it is. I don't know anything about it. But for the harmonic fan, we can do it. Why? Because it turns out that the harmonic polytope is a Minkowski sum. This is the definition of a Minkowski sum of 2 polytopes. P plus Q is the set of sums of a point in P and a point in Q. And whenever you have a polytope that is a Minkowski sum, this theory kicks in by Bernstein, Chovansky, and Hrushniako that tells you that finding volumes, and in particular this theory of mixed volumes, ends up being reduced to counting solutions to polynomial equations. You can decide what reduction is what. I mean, usually this is used in the opposite direction, where people are trying to count solutions to polynomial equations, and they use it by saying, okay, if I want to count these solutions, that reduces to finding some volumes. We do this in the opposite direction, and this was inspired by work of Postnikov. And we said, okay, maybe we can find the volumes by counting solutions to some system polynomial equations. Okay. The theory goes a little bit like this, that the volume of a Minkowski sum is the volume of each summand plus something called a mixed volume. And the mixed volume, for example, of these 2 polytopes, this is a triangle, and this is a triangle, these are convex holes, is equal to the number of solutions to a system of equations where you write a polynomial equation for each polytope, where you use these as exponents. So 0, 0 gives me a 0, 0, and so on. You put arbitrary coefficients, generic coefficients, not arbitrary, but generic. And then you see how many solutions this has, how many isolated solutions this has, and it turns out to be exactly the volume that you're looking for. Okay, that is the strategy. You're right, anonymous attendee, that the pink polytope has 6 vertices. The point in the middle does not count as a vertex. Okay, so what is it that we get there? By the way, I do want to emphasize that computing volumes is a tremendously hard thing. This is a sharp P complete problem. If you can solve it, you will have solved P equals NP. You will have become famous. You will make capitalism collapse, which might not be a bad thing. And there's a lot of other consequences. But basically, this is a very hard problem to do for arbitrary polytopes. And you can, at best, hope to be able to say something about particular polytopes. Okay, and so for this particular polytope, we can do something. So this harmonic polytope ends up being given by this Minkowski sum of a bunch of segments, which, if you've seen the permutahedron, this is a permutahedron. This is another permutahedron, but this is a permutahedron in the first n coordinates. This is a permutahedron in the second n coordinates, and then this is some simplex that's kind of like atravesada. What's the word for this? It's like it's just like stuck in the middle of the two. So you have something in the first n coordinate, something in the second n, and then this thing that's like stuck in the middle that breaks all the standard techniques. But we still were able to work with it, and we were kind of grateful for this term because it produces some very beautiful algebraic combinatorics. And what we ended up finding is that the volume of this polytope is given by something that it's complicated, and this is the best you can hope for often in these kinds of situations. It's a sum over all the connected bipartite multigraphs. I'll do an example of this. It's a sum over graphs of, this is basically like the degrees of the vertices in the graph. This part is easy to compute. This is the denominator is easy to compute. The numerator is tricky because this is actually the degree of a toric variety. And it's something called the toric variety associated to the toric ideal of the graph. Okay. There's a nice result that says that toric variety can be computed by counting lattice points in a polytope. So that's an alternative way of doing that if you prefer doing it that way. To give you an idea of what a particular term looks like, a particular term is a graph like this. It's bipartite, so it has top vertices and bottom vertices. The edges are 1 up to n. And then you get this toric ideal, where basically for every cycle, every cycle goes up, down, up, down, up, down, because this is a bipartite graph. And so you do the up edges minus the down edges. So 1 and 3 minus 2 and 4. This cycle gives you 5 on the way up minus 6 on the way down. And so each cycle gives you a product of the z's that you met on the way up minus the product of the z's that you met on the way down. So it's always a monomial minus a monomial. So you get a binomial ideal. This is a toric ideal, and then you get the degree in the sense of algebraic geometry. And there's a nice theorem that I think I won't have time to really describe, which basically says that if you want to do that, then instead you can compute this polytope, which can be, so it's a trimmed generalized permutahedron that can be obtained easily from this picture. And I think I don't have time to give you the definitions, but I think the point that I want to make is that this computation I can do in my head, actually. It's about the largest one that I can do in my head, but it's a little bit easier than computing the degree of a toric variety. But in fact, I mean, there's software that knows how to do this. There's software that knows how to do this, and so with either of these formulas, you can kind of feed it into a computer, and it does it, which is what you need, at least to some extent. We haven't studied, because computing volumes is sharply complete. We actually cannot expect that this can be done in polynomial time, and that's another question that I haven't answered to. Is like that we don't have an answer to is whether this volume can be computed in polynomial time. We don't know. Okay? We have a combinatorial formula that can compute it for the cases that we're interested in, but this might just be like impossible, not because we cannot do it, but because maybe there's a theorem to be proved that this cannot be done in polynomial time. Okay. And just to tell you, this graph comes from this mixed volume. Okay. Which are the summands that I was telling you earlier. Okay. And I think that I should probably stop here. So there's a nice picture that I'll leave you with, and thank you for your attention.
Thank you. That was a really great talk. Why don't we first, I'm going to open it up to questions. Let's first thank Federico by typing clap in the chat. Don't do it in the Q&A because we want to keep those separate, but do it in the chat. Type your claps. And then, so if you have a question, let's have people, you can raise your hand if you want to ask it yourself, or you can type it in the Q&A and we can ask it for you. So either one. Okay, looks like Theo has a question. Theo, do you want to, I guess I can't make you, unless you raise your hand, you can't say it. So I can read it out loud. Oh, okay. Are you raising your hand? Sorry. This is my first time doing this with so many attendees. Raise your hand again, Theo. Sorry, I like lost. Okay, I'm just gonna say it out loud and I'll figure it out. Okay, so Theo asks, are any of the two stratifications of the bipermutahedral fan related with, i.e. maybe equivalent to some refinement of the Fox-Neuwirth stratification of the configuration space of endpoints in the plane? If not, could they, the two new stratifications, lead to a different new presentation of the braid group Bn on n strands?
Thank you for that question, Theo. I really like it, and the short answer is I don't know. The longer answer is I don't know what the Fox-Neuwirth stratification is, and I would love to learn. I assume from what you're saying that it has to do with presenting the braid group, and that sounds like a lot of fun. So
I don't know if you can hear me now from
Yes.
right. Sorry, it's just that it records when the points have the same vertical position, and it records when they have the same horizontal position. So abstractly, it's a little bit similar, but different than what you're saying. It looks as if it's recording less information. And yes, Fox and Neuwirth, they used it to give a nice presentation for the braid group, the Artin presentation for the braid group. So I was thinking maybe, because it's the same space, it's the configuration space of points, and I was thinking maybe the stratification that you have can have a different presentation.
that's super interesting to me, too. I guess from either of these stratifications, you can tell when points are vertically or horizontally aligned. So I guess the answer is that these stratifications are both finer than the one that you're mentioning. And I would love to talk to you about what this would mean for the braid group. I don't know anything about that, but I really would love to talk to you about this more.
Sure, it'd be nice.
Sarah, if you want, I can read the question so you don't have to.
Okay, no, I think I figured it out. I realized if you raise your hand, you go to the top of the list. So Bishal, if you want to speak your question, I now think I know how to deal with it. Okay, Federico, I'll let you read it then.
Yeah, so the first question, okay, so clearly Bishal knows more than me about proving that things are real rooted, and I actually don't know what you mean, Bishal, but I do remember that this thing about poly frequency sequences is one of these methods for using that people use to prove real rootedness and log concavity. This is not what we use, although it might be related. I don't know the answer to that. And then Bishal's other question is whether this can be done in higher dimensions, because I'm doing it in the plane, but could we do a similar stratification in n dimensions? And I have to say that this is the question that I'm asked every time I give this talk, and I feel like we should answer it. I don't have an answer. I've never tried, to be honest, because let me say one sentence about the geometry. The geometric model that this is related to is that given a matroid, there's something called the wonderful compactification of the arrangement. If the matroid is realizable, you need to put a bunch of adjectives in front. But for a matroid, you have this space, which is the wonderful compactification. It lives in n dimensions. And the geometry of what we're doing here is that we are considering the conormal bundle over that, which has another n dimensions. And so if that means nothing to you, the point that I'm trying to make is just that like the first n dimensions, which is where the permutahedron lived, comes from the kind of classical wonderful compactification, and then we need the additional n dimensions because we're going to the conormal bundle. But there's a specific reason why we're going to 2n, not to 3n or 4n or whatever, and that's why everything happens for us in double the dimension. And for that reason, like we just didn't have a reason to think about this for higher dimensions, but there may be reasons, and there's certainly combinatorial reasons. And actually, there is work, I believe, of Sheila Sundaram that is related to the enumeration of permutations. So for the permutations, they can make a lot of sense. To instead of in bipermutations, a number can appear only twice, but you could say it can only appear 5 times, and then do the enumeration. And I think Sheila Sundaram has some results, enumerative results about that. And so there might be a matching geometry. That would be another great thing for somebody to look at. And let me say something else about my philosophy of doing combinatorics, which you didn't ask for, but you invited me to speak, and so I hope you don't mind if I get philosophical for a moment. Just like I think that we as combinatorialists can learn a lot from talking to people in all areas of mathematics, and whenever they see things that become too intricate for they start getting a headache because the combinations are getting too complicated, that's when we can come in and we can do a really great collaboration. And those kinds of problems tend to lead to very beautiful combinatorics. Having said that, I also believe very firmly that by doing the beautiful combinatorics that our community has been doing for decades, we very often see things that are so beautiful that they have to be connected to other parts of mathematics. And so I think that if you can take this and do the combinatorial story, and if it is beautiful enough, then I feel like it's almost guaranteed that there's going to be a matching geometric story that will be worth studying too. Okay, so Gaurav is asking about the relationship between the two fans and what does this mean for matroids. This is a great question, and I had a bunch of other slides that I cut because I knew that I was going to be running out of time. But let me say one word about that, which is that here I mentioned that this conormal fan associated to a matroid lives in the bipermutahedral fan or in any subdivision of the harmonic fan. So what does this mean? We have a new paper that I want to announce out loud so that we feel forced to finish it soon. It's been almost finished for a very long time with June and with Graham, so the title of this paper is Lagrangian Combinatories of Matroids. And the idea is that basically, because the conormal fan lives inside the bipermutahedral fan, you end up having to understand the way that matroid objects interact with bipermutahedral objects. And so, for example, you need to understand what is a bisequence in the world of matroids. So then you're led to the definition about biflat. Okay, and then you get these kind of cryptomorphic notions of matroids that come from understanding how this particular matroid, that is one matroid, or that is any matroid on size n, interacts with this, which is the same fan for all the matroids of that size. Okay. Now, we could do this actually for the harmonic fan or for any simplicial subdivision of the harmonic fan, and that would lead to a parallel theory. So instead of biflats, you would get like, I don't know, like what is a harmonic triple for a matroid? I think there probably is a notion of what is a harmonic triple for a matroid, which is explaining how the conormal fan interacts with the harmonic fan. And then it becomes a matter of just like, where does the we have some theorems to prove. So we had to prove some lock and cavity theorems. We had to prove some of the combinatorial Hodge theory, and we just needed to find the simplest possible combinatorics. So the harmonic fan, in some sense, is more essential. The harmonic fan has the universal property that this technique can only work for anything that is the harmonic fan or finer. But within that realm of things that are the harmonic fan or finer, we needed to find the simplest possible object, and the harmonic fan actually was not simple enough. And because it's not simple, as I was saying, it's literally not simple. So we need something simpler, which is simple, and that's why we need to go to the bipermutahedron. But you could study a different subdivision, and that would give you a kind of a parallel theory that I think should lead to some interesting matrix theory as well. And so one open problem that we have in this paper on harmonic fans is just, this fan is a simplicial subdivision of this one, but there might be others, and that should lead to parallel matrix theories, and that might be worth studying. So I hope I answered your question, Gaurav.
So maybe before, because we're starting to run into our next session, so maybe I'll give the link here for the next session. We're changing formats, so this will be a normal Zoom room, so you'll be able to have your camera on and stuff. And we're gonna do the puzzle hunt, which will be really fun. But maybe I can stick around, I guess, because for this last question from Ashley, and then if you have more questions for Federico, I invite you to try to talk to him or email him, or I don't know, is there a time? Yeah, well, I'll say email.
Yeah, feel free to email me with questions. So, okay, let me try to answer Ashley's last question. So, do any of the counts on faces of the bipermutahedral fan and or harmonic fan relate to bi-Catalan combinatorics? And again, Ashley, I'm afraid that the answer is I don't know. And actually, I don't know about bi-Catalan combinatorics, and I don't know if you are interested in telling us a little bit about it, or we could also talk about it offline, whatever you prefer.
Ashley, if you raise your hand, I think I now know how to make people talk. So if you want to tell us about it. Okay, you should be able to talk. I think you may have to unmute yourself though.
You look unmuted, Ashley, but we can't hear you. I'm not sure why.
Yeah, she shows us unmuted, but she might
Can you hear me now?
her microphone.
Yes, now we can hear you.
My headphones have decided to be quite problematic today. So I will admit I don't know very much at all about Coxeter biCatalan combinatorics, but my advisor is Nathan Reading, and I know he's like done stuff with that. And so it's just like, I don't know, this is a thing I've heard about. And so like, I was just curious to know. My sense is that there's like a twin version of every, so like for the Coxeter, for each finite Coxeter group, I think there's like a bi version of it. And so like, it's just like a funny kind of symmetric twin version of all the stuff. And I think it's still a young thing. So I don't know if there's a lot out about that.
Okay, thank you, Ashley. You are helping me. You're getting me very excited about your question, because I guess what, at least in my mind, what this connects to is that the permutahedron has another cousin polytope, which is the isosahedron, which is like the Catalan polytope. So there's like in factorial combinatorics and Catalan combinatorics, and there's the permutahedron and the isosahedron. And so I guess one way that I might rephrase your question is there something like a bi-isosahedron? I would love for there to be. If you find it, please tell me. And I think that's really interesting. And similarly to your other point, there is a permutahedron corresponding to any finite Coxeter group. And so another question that I hadn't asked myself, but you're getting me very excited about is there like a Coxeter version of the bipermutahedron? I think those are all really interesting questions. And if anybody finds answers, I would really love to hear.
Thank you so much.
All right, so maybe let's thank Federico again if we're still here in the chat by clapping. Yeah, thank you. That was a really great talk and a really good way to start off this conference.
Thank you all again so much for putting this together and for the very thoughtful way that you all are organizing this. It's really inspiring to see, and thank you everybody for your questions, and I'm excited to hear more about your work.